Welcome to the deep dive. Today we're taking a flashlight into some really dark corners of the digital world, looking at the code that, well, runs your hospitals, your banks, even Mars rovers. We're talking about ghost code. These are, absolutely essential systems, mission critical stuff, but they run on programming languages that are frankly invisible to most developers today, often decades old, super specialized.
Yeah.
And our source material digs into the top 5 most obscure languages that are still in heavy actual production use right now. And the point of this deep dive, it isn't just to make a list, right? It's about understanding this core trade-off.
Yeah.
Why stick with these hidden, maybe complex systems instead of updating?
Exactly. When does that raw performance turn into, a strategic risk?
That tension seems key, performance versus risk.
It is. And to even get on this list, the language had to meet some really strict criteria based on our sources. For obscurity, fewer than 5% of devs tagging it on Stack Overflow.
Okay, that's low.
And less than 2% of public GitHub repos using it. So this weeds out, the hobbyist or purely academic weird languages.
Right, so they have to be niche, but actually used for important things.
Precisely. And the real-world use bar was just as high. We needed proof of a publicly known production system, think critical infrastructure, aerospace, finance, regulated stuff.
Okay.
And it needed an active community behind it, not just historical interest. So a compiler release in the last couple of years and at least 100 active professional members. These are working tools, not museum pieces.
Got it. Okay, let's dive in. The first one is hiding in plain sight in healthcare. MUMPS or M?
Yeah, MUMPS. It first showed up back in 1966, Mass General Hospital. And its design, it really reflects the limits of that time. The key thing, the really distinguishing feature, is that the language is the database.
Wait, what?
Yeah, there's no separate database system like you normally think of, like SQL or something. It uses this integrated hierarchical sparse array database.
Okay, hold on. The code and the data are basically the same thing. In sparse array, what does that mean in practice?
Okay, think about patient records. Most patients don't have every single possible test result or field filled in, right? The data is sparse.
Right, makes sense.
So this structure is incredibly efficient for that. It's like an early, super optimized way to store nested data without wasting any space on empty fields. Perfect, really, for patient charts.
And the scale is just huge. The sources point to the VA's VISTA system. That handles healthcare for millions of veterans. It's kind of shocking that a language from the 60s is running the core clinical and pharmacy systems for something that massive.
It is. It's about scale, but also regulatory inertia. MUMPS is also deep inside some older modules of the big Epic electronic health record system, too.
So why hasn't it been ripped out and replaced?
Well, 2 big reasons. 1, the performance for this specific kind of data is actually really, really good. And 2, maybe even bigger. Replacing it means a massive, hugely expensive recertification process for that critical healthcare software. It works, it's certified, and the risk and cost of messing with it are just too high.
So the lock-in isn't just technical, it's bureaucratic. Okay, from hospitals, let's jump about 140 million miles to Mars, segment 2. Fourth, the Martian language.
Yeah, fourth is from 1970, and it is like the definition of minimalist. It's stack-based, like an old HP calculator using reverse Polish notation, pushing data onto a stack to work on it.
Right.
This makes its actual runtime incredibly small. We're talking often less than 8 kilobytes. It's tiny, it's efficient, it's interactive.
8 kilobytes. That's nothing. Fits on a chip the size of your fingernail. And you're saying this powers complex robots millions of miles away.
It does. The sources confirm fourth is in the flight software for several NASA Mars rovers. Pathfinder, Curiosity, they're mentioned specifically. It handles things like low-level control, reading sensors, and critically fault tolerance routines.
That seems like a place where, extreme simplicity is a massive advantage. But, okay, if it's so lean and reliable, why don't we see fourth in every smart thermostat or IoT gadget? Why use heavier stuff like Python or C++?
Well, that's the trade-off. Fourth can be tricky to write and maintain for just general purpose stuff, but for those deeply embedded systems where memory is incredibly tight and you need absolute deterministic real-time behavior.
Meaning it has to finish a task in a predictable time every single time.
Exactly. No operating system getting in the way, direct hardware access. That's where fourth still wins. It's used in things like high-end oscilloscopes, signal generators, even Intel firmware for that kind of rock-solid, predictable control. It hangs on because nothing else quite matches that minimal, reliable footprint.
Okay, fascinating. Let's pivot now. to the world of finance, where speed isn't just important, it's everything. Measured in nanoseconds sometimes. We're looking at the finance twins, J and KDB plus Q, also known as K.
Right. These two really dominate in high-stakes quant finance. And the reason is simple. They're built for expressing complex math and handling insane amounts of time series data at, well, blistering speed. Familiarity takes a backseat here.
Let's start with J. I've seen snippets, and it looks, well, barely looks like code. More like, I don't know, math symbols.
Yeah, it's quite something. J is an array programming language. Its whole deal is super powerful support for vector and matrix operations. You can express entire financial models, complex math, in basically a single line of this very terse code.
Which must save time in development and review, I guess.
A huge amount of time, especially for the kind of linear algebra that dominates quantitative finance.
And the performance has to be there. Sources say Citadel Securities uses J for, like, rapid algorithm prototyping, and Barclays for risk systems crunching over 10 terabytes of market data daily.
And its survival comes down to pure raw speed. J has this just-in-time compiler that takes those dense array operations and translates them directly into SIMD instructions.
SIMD, single instruction, multiple data.
Right, so the processor can crunch a whole bunch of numbers in parallel with one instruction. This gets J's performance for analytics workloads really close to optimized C code.
That's a serious technical edge.
Yeah.
Okay, what about its sibling, KDB plus Q? That sounds less like just a language, more like a whole machine built for speed.
That's a good way to put it. KDB plus Q is really an integrated system. It's a vector-oriented, in-memory columnar database bundled with its own language, K, and a query language, Q. It was purpose-built for high-frequency trading.
Meaning
ingest, store, and query literally billions of rows of time series data like stock ticks with latency under a millisecond.
Sub-millisecond.
Yeah.
Wow. So J is for writing the math fast, K is for handling the data fire hose instantly. Can you give us an example of that scale?
Sure. Bloomberg uses KDB plus Q for their core market data cache. Think about all the price updates flying around globally. KDB plus handles over 10 million updates every second for them.
10 million a second.
Yeah. And the CME group, the big futures exchange, uses it for storing their order books. In that world, a millisecond delay can mean millions in lost opportunity.
So pulling back, what's fascinating is that these languages, J and K, they only survive because the cost of not having that extreme speed is way higher than the cost of dealing with their obscurity.
Absolutely. That unmatched time series performance is their shield. Plus, there's significant ecosystem lock-in. A lot of proprietary trading models and risk calculations are deeply tied into KDB plus logic. Migrating away would be astronomically expensive and risky.
Okay. Moving to our final language. This one seems defined purely by, well, safety, ADA.
ADA, yes. First appeared around 1980, actually pushed by the U.S. Department of Defense, but it's still very much alive. There was a new revision, ADA 2022, quite recently. It's strongly typed, modular, and just built from the ground up for reliability and safety.
How so? What's its distinguishing feature?
It puts a huge emphasis on catching errors at compile time before the software even runs. It has extensive checks and this concept of formal contracts.
Contracts, like legal documents.
No, not exactly. Think of them as guarantees you write into the code. Like, this function requires this condition to be true before it runs, and it promises to ensure that condition is true when it finishes. It forces a very rigorous way of thinking and coding.
So basically, if something absolutely cannot be allowed to fail, you reach for ADA.
That's its whole reason for being. It's mandatory in many ultra-safety critical systems. Airbus uses it for flight control software, which needs that really stringent DO-178C certification.
We hear those certification names like DO-178C. What does that actually mean for the software?
It means you have to provide rigorous proof that the software behaves correctly under all defined conditions, that it's essentially free from certain kinds of errors. DO-178C is the standard for avionics, but there's also IEC 61508 for general functional safety. These standards basically demand languages like ADA that minimize runtime surprises.
Because a runtime surprise in a jetliner is bad.
Extremely bad, yeah. So if the ADA code compiles, you have a very, very high degree of confidence it will do exactly what it's supposed to. That's why the European Space Agency uses it for satellite software, why it's in critical defense systems like radar processing.
Okay, so we've got MUMPS in healthcare, Fourth on Mars, J and K in finance, ADA in the skies. Looking across these five, what are the common threads? Why haven't they just faded away like so many other old languages? Why has the obsolescence clock kind of stopped for them?
Yeah, if you synthesize across the sources, a few key themes pop out. First, every single one has a really strong domain-specific performance edge.
Right.
MUMPS is just incredibly efficient for those sparse medical records. KDB plus Q is unbeatable for time series data. Ada gives you that deterministic safety. General-purpose languages like Java or Python, they just can't match them in that specific niche.
And the second point seems huge. Regulatory or certification lock-in.
Oh, absolutely. Often that's the main reason they persist. The sheer cost, the time, the risk involved in recertifying a flight control system or a core banking application after rewriting it, it can run into hundreds of millions, take years.
You stick with the devil you know.
Pretty much. If it works, it's certified and it's reliable, the enormous risk of changing it often outweighs any potential benefit of using a more modern language that isn't as specialized.
And third, these aren't just relics gathering dust. They have active communities and tools.
Crucially, yes. They are living languages, even if niche. You see active, focused communities. The sources mention a 1,200-member MUMPS Google group, an 8,000-member Slack channel for KX systems.
Oh, okay.
And there are vendors providing supported tools like GNet for Ada, YadaDB for MUMPS. These tools get updates, security patches, they're maintained. And often you find these languages embedded inside larger modern systems written in C or Python, acting as powerful specialized scripting engines.
But all this stability, this specialized performance, it leads right back to that core problem we talked about at the start, the strategic risk. The sources mention this, right? The systems might be stable, but the knowledge needed to keep them running maybe isn't. Sounds like a ticking time bomb.
That is the critical vulnerability, yes. It's the aging workforce. Many of the developers who really mastered these languages, who built these systems, are nearing retirement.
Uh-oh.
So you have this shrinking pool of true experts who understand the quirks, the idioms, the deep-seated logic of these decades-old code bases.
And that directly means rising costs and more risk for the companies relying on this stuff.
Absolutely. Finding a skilled fourth or J developer. The market is tiny. Supply and demand kicks in, salaries go way up. But maybe worse is the knowledge gap. It slows down bug fixes, makes performance tuning harder, and makes onboarding new people incredibly expensive and time-consuming. They need months of specialized training you just don't get in universities.
So the industry is paying this huge premium just to keep the lights on for systems whose performance edge they feel they can't give up.
Yeah.
How are they dealing with this? Are they just hoping for the best?
No. They are reacting, but strategically. Where they can modernize without breaking the bank or failing certification, they're doing it faster. But where they can't, those core systems in finance, defense, healthcare, they're investing heavily. Things like formal mentorship programs, really trying to document everything, capture that institutional knowledge before it walks out the door.
Makes sense.
And they're also building stronger relationships with the few vendors left who specialize in these tools, like Adacore for Ada or NAX for KDB Plus DI, securing long-term support contracts because they know migration might not be feasible for decades, if ever.
So this deep dive really shows that counterintuitively, some of the most critical digital infrastructure isn't running on the shiniest new tech, but on these hyper-specialized, often obscure tools that provide such a crucial performance edge that the risk of their obscurity is, well, accepted.
It's a really fascinating trade-off, isn't it? You're relying on maybe just a few thousand people worldwide who truly understand these systems that impact millions, maybe billions of people, because they're the only tools fast enough or reliable enough for the job.
So what does this mean for you listening? If these languages, MU, MPS, Forth, JK, Ada, offer this kind of unmatched edge, whether it's pure speed or guaranteed safety, does that benefit ultimately outweigh the risk? The risk of relying on something so specialized, so understood by so few. When does that efficiency, that specialization become a liability that actually costs more than the speed it provides? Something to think about next time you check a stock quote or visit a hospital.
Until next time, keep exploring, keep questioning, and keep diving deep. Thank you for listening to today's podcast. Please feel free to click on the link in the description below to discover more podcasts.